guys, today's lesson is on simplifying perfect squares, in which we have done in the past. However, in this new section, we will be dealing with taking the square root of variables as well as numbers. So on the left side, on the column on the left, how do we get a number that's called a perfect square? Well, a perfect square is a number that results in squaring another number. So 2 squared is 4, in which 4 is a perfect square. 3 squared is 9, 9's a perfect square. 4 squared is 16, 16 is a perfect square, so on and so forth down the list. We have talked about perfect squares, or numbers that are perfect squares, previously in the year. Next to those numbers, we're taking the square root of a perfect square. Again, a perfect square is a number that we know the value of its square root. Square root is asking you what number times itself is equivalent to the number inside the root. So the square root of 4 is asking you what number times itself is 4. That would be 2. What number times itself is 9? That would be 3. What number times itself is 16? That would be 4, so on and so forth. If we're taking the square root of a number that's not a perfect square, we could simplify it using one of the perfect squares in our list. Over on the right column, this is our new topic for this section. And before we get to the actual problems, I just wanted to show you, this is almost kind of like a cheat sheet. Notice on the left side, we have all perfect squares and the square root of those perfect squares. That's obviously not every number on the number line. It's very specific numbers. On the right side are perfect squares with variables. Variables with an even exponent is a perfect square. We know how to take the square root of it. Now, as you can see, some of the answers are the absolute value of a variable, in which we have to remember if a square root of an even exponent results in an odd exponent, we're going to use the absolute value signs. So for example, in our first row and the column on the right, the square root of x squared is asking you what variable times itself will give us x squared. That would be x. Since we took the square root of an even exponent and the result was an odd exponent, technically it's x to the first, we're going to put absolute value signs around. Going to the next row, the square root of x to the fourth is asking you what variable times itself is x to the fourth. That would be x squared. Since we took the square root of an even exponent and the answer has an even exponent, we do not have to use the absolute values. Going on to the next one, the square root of x to the sixth. What variable times itself would give us x to the sixth? That would be x cubed. X cubed times x cubed is x to the sixth. We just took the square root of an even exponent and it resulted in an odd exponent. Therefore, we have to put absolute value signs around our answer. So in this sheet here, going further, just shows you all the square roots of perfect squares of variables. They have even exponents. This is then going to help us do the actual lesson for today, in which we will be simplifying expressions that are taking the square root. Sometimes we might not be taking the square root of a perfect square, in which we'll learn how to simplify it. This lesson will start off section 6.4. It's called nth roots because in this lesson we're going to be talking about square roots, and in the following lesson we're going to be talking about cubed roots. And again, we have the rule up at the top. If a square root of an even exponent results in an odd exponent, the value, our answer, will be using absolute value sign. So let's go ahead and check the first couple problems. Number 1, the square root of 49a squared. What I would recommend is to do the number first, the square root of 49, then the square root of a squared, and then we'll go ahead and kind of put those answers together. The square root of 49 for 49 is a perfect square. What number times itself is 49? That would be 7. And what times itself will be a squared, or the square root of a squared? That would be a. Once you get your answer, ask yourself, did we take the square root of an even exponent in which the result came out to be an odd exponent? Yes, that did happen, since a squared, the square root of a squared is a to the first, or the exponent of 1 is odd. We have to put absolute value signs around the variable. Just the variable, not the coefficient. Moving on to problem number 2. What number times itself is 81? That would be 9. What variable times itself would be b to the 4th? That would be b squared. Do we need absolute values in number 2? No, we don't. Because although we took the square root of an even exponent, the result also has an even exponent. Problems 1 and 2 were examples where we're taking the square root of expressions that are perfect squares. What expression times itself will give us 49a squared for problem number 1? That would be 7a. 7a times 7a is 49a squared. What expression times itself will give us 81b to the 4th in problem number 2? That would be 9b squared. 9b squared times 9b squared is 81b to the 4th. Moving along, we're going to hit some expressions that aren't perfect squares. We're going to have to simplify it to the simplest radical form. So again, just like problem 1 and 2, let's first take the square root of 40 in problem number 3. What number times itself would be 40? We actually can't answer that because 40 is not a perfect square. So what we're going to do, if you remember a couple of chapters ago, we're going to simplify the square root of 40. We're going to use the biggest perfect square that goes into 40 in order to simplify, which would be 4. We could rewrite this as the product of the square root of 4 times the square root of 10, or the simplified radical expression would be 2 root 10. Let's now go ahead and simplify the square root of x to the 4th. What expression times itself will give us x to the 4th? That would be x squared. How am I going to put these two pieces together? Since the 2 root 10, 2 is on the outside and the 10 is on the inside of the radical, and the x squared is on the outside, the one expression that we could answer the simplified radical form for the square root of 40 x to the 4th would be 2x squared root 10. We're just really putting those two values together, in which the 2 and the x squared are outside the radical and the 10 would stay inside the radical. Do I need to use this absolute value signs in this case? No, I do not, because when I took the square root of a positive exponent, the result was also a positive exponent, or an even exponent. When we took the square root of an even exponent, the result was even. Let's check out problem number 4, in which we are now adding some variables. The square root of 50 can be simplified. It's not a perfect square, but the biggest perfect square that goes into 50 is 25 times 2, in which the simplified expression 5 root 2 would express the square root of 50. Let's now do the square root of x squared. What variable times itself is x squared? That would be x. And since we took the square root of an even exponent in which the result was odd, we're using absolute values for that result. And lastly, let's go ahead and take the square root of y to the 4th. What variable times itself is y to the 4th? That would be y squared. No need for absolute value signs. An even exponent, it stayed even in the result, no absolute value signs. How am I going to put now these three pieces together to answer our question? What's the square root of the expression 50x squared y to the 4th? I'm going to put everything that's not in a radical outside the radical, and everything inside a radical, inside a radical. So we're going to have 5 absolute value of x, y squared. And the only thing inside a radical in all 3 of our expressions is just 2. So our final result or expression is 5 absolute value of x, y squared, root 2. Moving on to problem number 5, we're now going to hit variables with an odd exponent in which we could simplify taking the square root of. Although it's not a perfect square, just like in the last 2 problems when we had the square root of 40 or the square root of 50, we could also simplify the square root of a variable that's not a perfect square. So let's go ahead and take the square root of each individual part, the coefficient and each variable x squared and y cubed, in which I'll first start with the square root of 4, in which we know is 2. The square root of x squared, what times itself is x squared? That would be x. And since it has an odd exponent, we're going to use the absolute values. And lastly, here's a new part, the square root of y cubed. We don't know what variable times itself is y cubed, but we can simplify it. What's the biggest perfect square that would go into y cubed? That would be a variable with an even exponent. So the biggest one that would go in was y squared times the square root of y. Simplifying the square root of y squared, we'd get the absolute value of y, root y. Since it's not a perfect square, we still have the radical in our expression, but it's now simplified since the variable inside the radical has now a smaller exponent. Let's go ahead and now put all these pieces together. Again, everything outside the radical will go outside. So the 2 absolute value of x and absolute value of y are all outside a radical. In our final answer, they will appear outside a radical. And the only thing inside a radical in all 3 of the pieces is root y. So we're just putting all 3 individually together to get our final expression. Let's go ahead and move on to problem number 6, in which we see all 3 of these parts of the expression, the coefficient in both variables, none of them are perfect squares. So let's talk about each individually, in which the first thing we'll take the square root of is 24. What's the biggest perfect square that would go into 24? That would be 4 times 6. That would simplify to 2 root 6. What is the square root? So the next part would be the square root of x. What times itself would give us x? That would be nothing. The square root of x actually can't be simplified any further because there is no perfect square or variable with an even exponent that goes into it. So we can't simplify that any further. And the last piece, the square root of y to the 5th. What variable times itself is y to the 5th? There isn't any. A variable with an even exponent is a perfect square. We can, however, simplify this just as we did in problem number 5 when we did the square root of y cubed. However, the biggest perfect square that would go into y to the 5th is y to the 4th. The biggest even exponent that would go into it times y. The square root of y to the 4th is y squared. Root y we can't simplify any further. Let's put all 3 of these pieces together. What are all the expressions that will be outside the radical? That would be 2 and y squared. So we have 2y squared. Root x and y will go inside to make one expression as the result of the square root of 24 xy to the 5th. The last three problems, we're just adding some variables. For example, problem number 7, we now have 3. Let's go ahead and take the square root of each individual piece. First one starting with 32. Where 32 is not a perfect square, we're going to ask ourselves, what is the biggest perfect square that would go into 32? That would be 16 2 times. The square root of 16 is 4, in which the square root of 32 reduces to 4 root 2. Let's move on to the square root of x squared, in which we now know is the absolute value of x. I know it's the absolute value because we took the square root of an expression with an even exponent, and the result was an odd exponent. The next we'll do the square root of y to the 4th, which we know is y squared. No need for absolute values there. And lastly, we'll do the square root of z cubed, which we kind of already saw in problem number 5 with the variable y. The biggest perfect square that goes into z cubed is z squared times z, or the absolute value of z root z. Let's put all the pieces together to write it in one expression. All the outside parts would be 4, absolute value of x, y squared, absolute value of z. 4, absolute value of x, y squared, absolute value of z. Everything inside the radical would be the 2 and z, so the square root of 2z. What I'm going to ask you guys to do is pause the video, try problem number 8 on your own, and then go ahead and play the video to check your answer. Here is our answer for problem number 8. The square root of 162. 81 is the biggest perfect square that goes into 162 2 times, in which that would result in 9 root 2. The square root of x cannot be simplified, therefore the x is staying inside the radical. The square root of y squared is the absolute value of y. And to simplify, the square root of z to the 7th, the biggest perfect square that would go into z to the 7th is z to the 6th times z. The square root of z to the 6th is the absolute value of z cubed. We took the square root of an even exponent, in which the result was an odd exponent, root z. Therefore, in our final answer, we have the square root of z cubed on the outside and z still inside the radical. The last problem I wanted to go over with you guys is problem number 9. We have the square root of an expression raised to the 4th power. This is actually not as difficult as it may look. Something raised to the 4th power. What times itself would be something raised to the 4th power? It would just be this expression squared. 32x squared, or times itself, would be that expression raised to the 4th power. We don't necessarily have to expand on this one. You don't have to square the inside expression. It's just the idea, if you have something to the 4th power, what times itself would be raised something to the 4th power? It would be that same expression squared. That will conclude our lesson for today, just simplifying square roots with both coefficients or numbers and variables with different exponents in it. Please let me know if you guys